This test is set up to load the sample up to 40 pounds first, and then it zeroes everything out. Loading to 40 pounds, make sure that we take out any slack that is in the setup, the load string. I'm going to get a message here pretty soon to remove the extensometer. It will notify me to remove the extensometer once we've reached the yield point based on a 0.2% offset rule. There's the message. Note that the test does not stop running when we remove the extensometer. It keeps going, but you have plenty of time to remove it. All of the materials that we test are very ductile, and so there's plenty of time to remove the sample before, or pardon me, to remove the extensometer before the sample breaks. Once we've passed the yield point, as you can see from the graph, we're going to be looking for the next significant point on the graph, which would be the tensile strength, the highest point of stress on the graph. This particular steel sample, as I mentioned, is 1018 steel, which is very ductile. In fact, when this particular type of material breaks, it's rather uneventful, and then it does not have any, or it has very insignificant pop as it breaks. It's a very gradual break with a very fibrous nature to it, and so it's not the most exciting sample to use in the lab. Instead, in the lab exercise, the handouts, you will notice that we use a chrome moly alloy, a 4000 series sample, which is a little less ductile, so when it breaks, it gives a little more of a pop. It's a little bit more exciting. I'd like to point out that the force is still going up. So if you look on the Blue Hill software, you'll notice that we're at 3491, 3493. The load is still going up. We have not reached the tensile strength yet, or the tensile point. That number will slowly increase, come to a stop. And then begin to head back down. I notice that the load now is beginning to teeter between 3525 and 3526. I would say at this point we've reached the tensile strength, and we should start to see that number drop down. So that's the end of our test. You can see that it broke. The audio is difficult to tell from the microphone that I'm wearing, but it didn't make much of a noise. You can see a very ductile fracture with lots of necking. It's very important to mention that the data has not been saved yet. You want to make sure that you hit finish sample. By the way, there's a next button right here in case you wanted to do more samples. We don't. This says, do you want to start another new sample using the same set of parameters? Your option, if you're running multiple of these samples in one lab session, which you probably are, in aluminum and in steel, for example, you could hit yes. I'm going to go ahead and hit no. Finishes up, takes me back to the startup screen where I can select a test. Notice since I just used that test, it now has it listed here, Engineering 151 tension with extensometer, and I could use that same profile again if I wanted to by just hitting next. I wouldn't have to hit browse. I'm going to minimize this and look at my desktop. On my desktop, I now have a couple of different files that I want to point out. Recall that I called this file name tension, and so there is a folder called tension. Inside that, I'll find the raw data. This is a comma separated value file, a CSV, so before you post it on crops, you probably want to save it as an Excel file. And the data that's in this file is the strain, extension, and load. It's important to note that students are going to have to calculate stress on their own. Load is given in pounds. They will need to calculate the stress given the cross-sectional area of this sample. Of course, strain comes from the extensometer. Extension comes from the cross-member position. Both sets of data are included because the strain data is not going to be throughout the full set of the test because we removed it at the yield point. So as I scroll down, I'm going to find that those numbers start to get a little bit crazy, meaning that once I remove the extensometer, the position was all over the place, and so the value is going to go kind of crazy. When you plot all this data, it will be very obvious where the extensometer was pulled off. Going back up to the top, again, extension is important because that goes throughout the entire test. It's not the most accurate data like the strain data is, but it's throughout the whole test. Generally, what the students will be asked to do, and this is specified in the lab handout, you are of course free to modify this, but the students are asked to create a full stress strain diagram based on the extension data and then a partial stress strain diagram based on the strain data from the extensometer. That will take them up to the yield point. It's a more accurate curve when they're asked to calculate Young's modulus and the yield point. Young's modulus will vary considerably if they use the data from the extensometer versus the extension from the cross member. The data from the extensometer will closely match that of published data for the steel. I'm going to minimize this file and show you a couple of other things. So again, this is the folder that had the Excel data. There's a PDF that if you try to open, it doesn't work. I'm not sure what it's supposed to be, and a Word file that actually is, there's a PDF version of that has what we want. So I'll spare you the time of opening those up and just get to this PDF. This PDF has the name that we implied, tension, but it has this extension on it, and that's how you can recognize it's the one that actually has data in it. This is the quick graph that I mentioned. This outputs load versus extension, so this is somewhat useful, but again, it does not have stress versus strain, which is what the students are asked to do. They are asked to make a stress strain diagram. But this is a recap of what the test was that we saw live on the screen. And this is strain data versus load. Of course, you see the strain data kind of goes crazy, as I mentioned, because at this point right here, the yield point, we took it off, and so we were handling the extensometer, and it was all over the place. And so it's not any good past the yield point. But again, the students will use the Excel data to make their own graph. I've opened up the Blue Hill software because I want to take a few minutes to show you the test profile that was created for this test. In a separate video, I'll go through more detail of how to create profiles, but if you want to modify anything for this test profile, I'll show you how to do that. To get back to the main menu, I'm going to hit the Blue Hill icon up here in the top left. That gets me back to this screen. I'm going to go to the method screen. The method screen is where we can open, access files, modify them, and I'm going to select the Engineering 151 tension with extensometer. If you did not see that in this list, again, you would go to Browse and go to the appropriate directory. Since I have the appropriate file highlighted, I'm going to go ahead and hit Open and walk you through a couple of things. First of all, we've specified in the very first menu, which is under the General heading in the Method menu. We specified U.S. customary units that can be changed to SI if you desire. There are a few other items here that I won't go into because I don't think they're the most critical. I'm going to jump down instead to the specimen category. In the specimen category, you can specify the dimensions of the sample. This is important if you're asking the Blue Hill software to calculate stress and strain, or stress more importantly. We are purposefully asking the software to not calculate stress. We want the students to do that themselves with the Excel data that we saw. So I have the data in here, but it's not terribly critical. I'm going to skip all of these input choices as well. I'm going to go down to control. I'm going to start with the pre-test button. You'll note, as I mentioned, I've specified a preload. I mentioned, I think, 40 pounds, but it's actually 20. I was mistaken about that. We've got this going up to 20 pounds when the test starts. Once it reaches 20 pounds and has pulled out any slack in the load string, we have it auto balance, meaning it stops for just an instance, it zeroes out the strain and force data and starts over, so that when it's plotting the load versus extension, everything starts from 0, 0 and ramps up nicely from there. For the control of the test, you'll note that I have it controlling the speed by means of the extension rate, that is the movement of the cross member, at 0.05 inches per minute. Seems to be a pretty good value for steels, aluminum, so on and so forth. In the ASTM specification for this test, I believe it's at least double that. This is good for a classroom setting. Now we have a second ramped value. When the extension, the extension rate will be 0.08 inch per minute once the extensometer is removed. We speed up the test after the extensometer is moved to speed things up. These metals that we use are so ductile it can take a long time, so we want to speed things up a little bit. End of test. We need to tell the software when to stop the test. In this particular situation, I've specified the rate of load option that you see. That means that when there is a decrease of 40% in the load value from one data point to the next data point, which, by the way, this is recording every half a second, as we'll see in the next screen. If it sees a drop of 40% or more, that indicates to the software that the sample has broken, and so that's when it's going to stop the test. That works really well for steels and aluminums. In the data menu, as I mentioned, we are collecting data every 500 milliseconds or every half second. We don't want to speed that up too much because in our Excel file is huge. If we speed it, or if we slow it down too much, obviously we're not grabbing enough data. Regarding strain, we are in fact indicating that we want the extensometer to be used, and that's why we indicate strain 1. If we did not want to use the extensometer and only the position of the cross member, we could select extension. I do want to remove the extensometer during the test. I don't want to leave that on when the sample breaks. The criteria is that when the offset yield is reached, it's going to give me a message to pull off the extensometer. How does it know when the offset yield is met? That's when it's 0.2% offset, as I had mentioned. What's it going to do? It's going to continue the test. You could have it stop the test. I've indicated that I want it to freeze the strain value at removal, meaning whatever the value of the strain is when it stops using the extensometer, I would like it to hold. That feature does not seem to be working correctly, as you noticed in the Excel file. After I removed the extensometer, I saw all those crazy values. Not sure what's going on there. I'm going to skip down and go to graph 1. In graph 1 on the x-axis, notice I'm intentionally having it put extension in inches rather than saying put the strain 1 value there. We want the students again to calculate strain themselves. Similarly, on the y-axis, I'm having it record load in pounds instead of stress, which it could do. Going down to raw data, I'm asking it to export the time intervals, every half second that is, the strain, the extension, which again, position of the cross member is what extension is, and load. That's what's getting sent out. In the reports section, I'm telling it to save the PDF document. I'm telling it what path to output it to, although when we run the test, we have the option of changing that. The PDF document, by the way, is that simple graph that I showed you. It's a quick look at the summary graph of the test itself, but I'm more interested in the exporting of the raw data. I go down to the raw data menu, I select export raw data as a CSV format. That's all I have to do. There are some other options in the test prompt. I'm going to skip that for now. This is the place where you can have it say things like, before you start, enter the following values of the sample, which, by the way, we have the material as one option that the students input. Recall that I had to put in steel 1018. You can have all kinds of things that it asks for. Before the actual test starts, I've entered this test prompt. I said I want to zero the load and strain values, and we want to reset the extension value. You can put in more to that if you'd like. If I had made some changes, I would hit save and close. That saves that test profile. If we're ready to run the test, we go back to the blue hill icon to get to the home screen, and now we can hit test. That concludes this tension test. If I wanted to at this point, I can take out the samples by loosening the grips. You can actually see that this did not physically break in two. Another reason I'm not crazy about using the 1018 steel and we've switched over to the chrome moly steel, it's brittle, or pardon me, weak enough that I can just separate it into two. If you'd like to run another test, it's all set to go. If you needed to remove the load cell to run another type of test using a different load cell, you would, of course, use the reverse procedure that I indicated when putting this together, removing the Allen bolt up here and removing the grips themselves. That's it for running the tensile test for Engineering 151, Strength of Materials, using the extensometer.